Everyone, thanks for coming. Today we are going to do a review of our week 13th lecture for the ODE course. So in this week, we introduced more about numerical methods for solving ODEs. So first, we make a comparison of the improved Euler's method and the Euler's method. Specifically, the improved Euler's method, which is also known as the Hughes method, improved on the previous Euler's method by using a predictor and corrector form. Basically, it is a two-step method. The local truncation error is big O(n) h cubic. You can see that it is based on the trapezoidal rule for numerical integration. The global error is OH squared. It is much more accurate than the Euler method for the same step size. Based on the Euler's method and the improved Euler's method, we can do an adaptive step size control to control the local truncation error. We use the improved Euler's method as an accurate solution, then we can estimate the local truncation error for the forward Euler's method. Then, after estimating the local truncation error, we can control the local truncation error below some threshold epsilon by adjusting the time step. Modern adaptive codes use this technique to optimize efficiency and accuracy and adaptively select the step size. Next, we introduce the Runge-Kutta 4 methods. The classic fourth order Runge-Kutta method, known as the RK4 method, approximates the solution using this four-stage calculation: K1, K2, K3, and K4. The local truncation error for this method is of order big O h5. The global truncation error is big O h4. It is much more accurate than previous Euler or improved Euler's method. The implementation of this explicit RK4 method is simple on a computer, and it also can be adapted to adopt variable step size. Specifically, if f depends only on the time variable t, RK4 reduces to the Simpson's rule for numerical integration. So this explains why the local truncation error is of order big O h5, and the local error is big O h4. Next, we introduced multi-step methods like the Adams method, Adams-Bashforth method, and the implicit Adams-Moulton method. The multi-step methods use previous points yn minus 1 to yn minus k in order to compute yn plus 1 using a polynomial interpolation for the derivative for y. Here we assume constant step size, but for the Adams methods, we are using adaptive Adams method to boost efficiency. If we use a polynomial to approximate y itself and to enforce the derivative of the polynomial to match the derivative for y at tn plus 1, then we obtain the backward differentiation formulas. Those formulas are also implicit implementations and are more stable compared to explicit methods. For the Adams-Bashforth method, it is explicit. It uses previous derivative values. The local truncation error is of order h k plus 1, where k is the number of time steps used for some lower order methods. For the Adams-Moulton method, it is implicit. Generally, it is more accurate than the Adams-Bashforth method of the same order. The local truncation error is of order h k plus 1, but the coefficient is much smaller. If we combine those two methods together, we would obtain the predictor-corrector scheme. For the backward differentiation formulas, they are implicit, and they approximate solution with a polynomial. They are very good for steep problems. The advantages of multi-step method is that compared to RK methods, they can repeatedly using the values at previous time steps to reduce the number of calculations required. However, many of those multi-step methods are implicit, which would require solving nonlinear equations on yn plus 1. The errors can propagate from earlier steps, which means we have to use some accurate methods in order to generate the numerical solution as the first few time steps. Finally, we talked about the stability issues and numerical concerns when selecting appropriate methods. First, we need to consider truncation error and round-off errors. That is to say, if we are using some lower order method like the forward Euler's methods, the round-off errors can accumulate, and sometimes the global errors will not reduce even if we use a very small step size. On the other hand, the stability issue remains a critical concern if we are solving if we are numerically solving ODE systems. So basically, we consider solving the problem y prime equals to ry when r is smaller than 0. We hope that the solution is asymptotically correct, which means that as t goes to infinity, the solution will also approach 0. So for the backward Euler's method, it is unconditionally stable. For the forward Euler's method, it is stable only if the step size is smaller than 2 divided by the absolute value of r. So for RK method and other methods, we can also perform stability analysis and derive the constraint on the step size edge. So when selecting the appropriate numerical methods, we wish to balance accuracy, stability, and computational costs. Generally speaking, implicit methods allow for larger step size and are suitable for steep problems. Variable step size and order would also help us satisfy error tolerance for the local truncation errors. Finally, the smoothness of the function f, the derivative for the solution, also affects the choice of the order of the numerical method. Thanks for listening.